Today we are going to discuss the NMR spectroscopies. NMR spectroscopy. This is called nuclear magnetic resonance spectroscopy. There are two types of nuclear magnetic resonance spectroscopies. Number one is proton, which is called HNMR. Proton means hydrogen. Proton or HNMR spectroscopy. Or number two is carbon-13 NMR. Proton NMR or carbon-13 NMR. Now, one of my teachers used to say one very interesting thing about the spectroscopies, any type. They used to say, these are the spectroscopies are our eyes to look at the molecules. What are they? They are eyes to look at the molecule. They are our eyes who look at the molecules. So it is kind of structural determination. These spectroscopies look at the molecules because the molecules are very tiny. We do not have any such gadget instrument or any microscope which can look at the molecule. So this is the thing which looks at molecule. और फिर हमें बताती है कि how do they look like? Methane, ethane, propane, butane, etc., etc. So this is the first time where we got to know about these. Right? This is I talked about the journal, all spectroscopies. There are many types. Nuclear magnetic resonance is one of those. So the basic idea behind you understood? From now on, for a week or so, we are going to see how these spectroscopies help us to look at the structure of the molecule. How they tell us that how these structures of the molecule look like. Do you get it? Okay, for example, let's see. For example, the first one is proton NMR spectroscopy. First, I'm going to give you the basics about it. Then I'll let you know how it is used to determine the structure. Right? Lalma, we are going through the spectroscopies now. Right? First, nuclear magnetic resonance spectroscopy is proton NMR. Now, what this technique says, there's an atom of hydrogen. Okay? If I have an atom of hydrogen, bacho, hydrogen's atomic number is 1 and atomic mass is 1. So how many protons? 1. How many electrons? And how many neutrons? 0. So if I draw an atom of hydrogen, there is only 1 proton in the nucleus, and there is only 1 electron which is revolving around the nucleus. Is it so? Now, you know, before 1981, we used to believe one thing, that the electrons, they revolve around the nucleus like this. And they also spin on their axis like this. And this electron is revolving and also spinning. Just like Earth revolves around the sun and spin in the axis. ऐसे ही हो रहा है. When it spins days and night, when it revolves, the weather's just like that. But we were thinking before 1981 that the proton in the nucleus is the silent, not doing anything, just statically sitting inside the nucleus. But that was not the case. What we figured out, that the proton in the center is also spinning. Obviously, it can't revolve, but it is also spinning. If a proton just like this is the proton. If it is spinning, there are two types of spin, either anti-clockwise or the same proton can spin clockwise, right? So in 1981, we found, the nucleus of an atom contains proton and it is also spinning. It is also spinning. And when in physics we learn, when a charge spins, it creates a magnetic field around it. So when this proton is spinning, it is creating what? A magnetic field around it. Just like that. If it is spinning like this, so it is a magnetic field around it. So in other words, let me put this like that, this way. Just I'm saying कि जो hydrogen का nucleus है, या hydrogen as an atom is like a tiny magnet. So from here on, we are going to believe that the hydrogen, any hydrogen in any organic compound is like a tiny magnet bar. Let's say methane has 4 hydrogens. So I assume that the methane has 4 tiny magnet bars. And when there is a magnet bar, one pole is what? North and the other one is south. I assume 2 of the bars are placed like this and 2 of the bars placed like this. Okay? So methane has 4 tiny magnet bars like this, 4 hydrogens. So from here on, Aris, what we are going to think? Every hydrogen is like a magnet bar. Now, these 4 magnet bars, because of their spin in opposite direction, 2 of them spinning clockwise, 2 of them spinning anti-clockwise. So I assume 2 of them as north face up, south down, north down, south up. This is so. Got it? 4 tiny magnet bars. Okay? If we place them in a bigger magnetic field, at this moment, although they're spinning in opposite direction, let me tell you one thing, but their energy level is same. If I draw their energy level, for example, here, this is energy. So what I'm trying to say, in the absence of any external magnetic field, the 4 tiny magnet bars, 4 tiny hydrogens, they are placed at the same level of energy like this. Okay? Now what I did, I placed these tiny magnet bars into a bigger external magnetic field. Just like imagine, you take a compass needle and put it in a bigger Earth's magnetic field. So compass क्या करता है? It has to align itself with the external magnetic field. But obviously they cannot. Let's say this is the North Pole and this is the South Pole of external bigger magnetic field. What happened? When you applied an external bigger magnetic field, 2 of them, these 2 magnets, found themselves luckily aligned with external magnetic field. Because in the North Pole, external magnetic field ke kis pole ke saath aa gaya? So they find themselves aligned. When they are aligned, they attract each other, they develop the attractive forces, and they stabilize. They get down in energy. So 2 of them two of them, for example, these two, are going to jump down to a lower level of energy, right? But on the other hand, these two, what happened to them? The North Pole, repelling North Pole, the South Pole, repelling. If they would have been a compass needle, वो तो switch कर लेती. They are not at this moment. They cannot. So they are repelling each other. Because of their repulsion, they excite. They excite and get to a higher level. Two of them get to this level. And the energy gap created between them here is delta E. So what I said, as soon as you take the methane molecule, one molecule of methane, you put it in external bigger magnetic field, it splits up into two sets of energy level. The protons, those which are aligned with external magnetic field. This is EMF mean bigger external magnetic field. Here is no EMF. And these are opposed with external magnetic field. So those which are aligned, those which are opposed, they are go like this. So what I did, again, coming back to the point, because hydrogen is a magnet bar, every hydrogen. So I have 4 hydrogen. I put them in a bigger external magnetic field. They split up into two sets of energy level. And this energy gap created between them, delta E, depends on two things. How much stronger external magnetic field I'm going to put them. But if I put them all in one external bigger magnetic field, like Earth, तो वो तो constant हो गया. The other factor that depends on how they are going to split apart is their environment. How these hydrogens are living. Are these the hydrogens connected with the carbon, or these hydrogens connected with oxygen? You know, environment mean how they are connected and what is around. Are they connected with the nitrogen? Something like this. Okay, so that depends on that. So this, what I'm trying to say, that this energy gap that has been created is not fixed for everyone. It has to be splitted. It has to be splitted. Okay, into two sets of energy level, right? Okay, now, so in the next moment, what I did, now I took 4 hydrogens, 4 tiny magnet bars, put them in external bigger magnetic field. They split up into two sets of energy level. Why? Because they were behaving like a tiny magnet bar. Some of them were aligned, some of them were opposed, so therefore they split up. Now what I did, I passed them radio waves, a kind of source of energy in an electromagnetic field, electromagnetic spectrum. There are different types of waves: ultraviolet, infrared, visible light, and this is another radio wave. When I pass the radio waves on them, these two, which are actually aligned and are at lower level of energy, they absorb radio waves and flip to higher energy state from this point to this point. And why I give the radio waves? Because the energy gap which is required for the flipping is actually the one which is equal to radio waves. So therefore, they absorb energy and flip to the higher. And when I collect this energy out, I'm explaining, and I collected it on a spectrum, and I found some part of energy missing. Here. I found some part of energy missing that appears in the form of this line known as peak. And this graph or spectrum is known as NMR spectrum. And this peak or this graph will give me information about these protons and will give me information hence about the organic compound structure. So now I'm going to say it all in one go. I said I have an organic compound which contains 4 protons. So I believed and I know these 4 hydrogens are like 4 tiny magnet bars. I place them into a bigger external magnetic field, which splits them into 2 sets of energy level, because some of them were aligned and some of them were opposed when I placed them in bigger external magnetic field. Then I, on purpose, passed the radio waves on them. And when I passed the radio waves, those which were aligned and were at the low level of energy, they absorbed some part of the radio waves, right? And flipped and gone to the higher level of energy. The part of the energy that radio waves were absorbed, obviously when these radio waves come out of this container, this one, when they pass and come out of this area here, that part which has been absorbed would be missing, So that will appear in the form of peak in NMR spectrum. And that peak helps me to identify the structure of that compound, right? So there's a blind compound that has been given. I just performed this thing and I was able to confirm what is that organic compound. Is it clear now? This technique is known as NMR spectroscopy. This technique is known as NMR spectroscopy. Now, let me show you the notes. Whatever I said, let me show you in words what it says, right? So look at this. Look at this. What I said, now I'm going to go through it one by one. What I said, first of all, the protons present in the nucleus of hydrogen, they spin and create a magnetic field around it, or it behaves like a tiny magnet. Sorry? Yeah, I will. You want me to share this document on the group? Yeah, I'll do it. So the protons present in the nucleus spin and create a magnetic field around it. So in other words, they behave like a tiny magnet bar. And methane has 4 hydrogens, I believed. And there are 4 tiny magnet bars here, right? And in these magnet bars, I assume some of them are north, some of them are south. And as soon as I place them in an external bigger magnetic field, automatically some of them found aligned and some of them opposed, because all of the hydrogens cannot spin in one direction. That's a very, very least possibility. Okay. So once until there was no external magnetic field here, they were at the same energy level. As soon as I place them in a bigger external magnetic field, they split up into 2 sets of energy levels. Those which are aligned went down, those which are opposed went up. These are the questions the examiner asked you, okay? And once they were broken down into 2 sets of energy level, what I did, I passed them through the radio waves. So those who were aligned with, and at the low level, they absorb energy and flipped to a higher level. That amount of energy that had been absorbed to flip would be missing when they come out, the radio waves.
Then will we flip the opposite one or the...
No, the one which are down, the aligned one. Yes. So then that part of energy would be missing. And missing energy will appear in the form of a peak in NMR spectrum. That peak will lead us, will help us to look into the structure of that compound. And this phenomena, this technique is known as Proton NMR spectroscopy. Because they are the ones, no, we are not looking at a line. We are looking who is at the low level of energy. And we gave them the gap exactly equal to the energy gap. We gave them energy. So they could flip, right? Okay, now the proton present in the compound may have a different spin, but some same energy level. So this is what I made clear. If the spin is opposite, the energy level is not the different. It is the same. When they are placed in a bigger external magnetic field, they split up into 2 sets of energy levels. Okay. Those who are aligned with external magnetic field, they get to the lower level. Those which are opposed, they get to the higher level. The energy gap created between them depends on what? The strength of external magnetic field, which we mostly keep constant, and the chemical involvement of the protons. When the radio waves are passed, the protons which are aligned are present at the low level of energy, absorb energy from the radio waves and flip to the higher level of energy. This absorbed energy appears in the NMR spectrum, and which is to determine the structure. This technique is known as NMR spectroscopy. And this is, I just imagined that this is an NMR spectrometer where I have this lamp that is producing this light, the radio waves, and then these lines showing there is a very strong external magnetic field all around, and then there is a place to put the sample in. That is a test tube kind of thing. That's a methane. So then as soon as I switch on the light, so the methane protons, they absorb some part of energy, and when it is collected on a spectrum, you see it appears in the form of the peak, and this peak helps us to determine the structure. Now the next question, technique basic samajh aa gayi. The next question, what about the NMR spectrum? The NMR spectrum, the one here, now we are going to focus on this. My question to you, okay, let me ask you a question. If methane has 4 hydrogens, so one thing that is clear, यहाँ peak किसकी होती है? Hydrogens की. यहाँ peak hydrogens की होती. So my question is, कि अगर मीथेन में 4 हाइड्रोजन्स हैं, तो would there be 4 peaks, or would there be 1 peak, or there 2 peaks or 3 peaks? ईथेन में अगर 6 हैं, ब्यूटेन में अगर 10 है,
especially 2 peaks because of the spin of the 2 magnets.
Now this thing, the rule is, no, every hydrogen does not have a separate or independent peak. It depends on the chemical environment of the peak, environment of hydrogen. All those hydrogens which contribute to 1 peak, which are in the same chemical environment, they always contribute to 1 peak. They always contribute to 1 peak, right? So the first rule is, whenever we look at the spectrum, now the actually question is going to come like this. They'll show you this spectrum, they'll ask you, okay, find out which compound is this. So first thing you will see, these lines known as peaks are representing hydrogen. And they are not representing one single hydrogen. They are representing what? The number of hydrogens contributing towards that peak. Okay? For example, it is look, the chemicals, all the hydrogens in the same chemical environment contribute to 1 peak. The area of the peak is directly proportional to the number of hydrogens contributing towards that peak, right? उतनी बड़ी peak होगी, right? Wider area of the peak उतना ज़्यादा होगा, right? Now look at this. For example, I ask you, okay, on that basis, can you tell me how many peaks in NMR spectrum for this compound, ethanol? Okay, this is a hydrogen which is attached with a carbon. So all those hydrogens which are attached with 1 carbon, obviously, surely, they have the same chemical environment. They are in the same chemical environment, so they will contribute to 1 peak. That's a common sense. So obviously, they are going to contribute to 1 peak. Is it so? So 3 hydrogens are going to contribute to 1 peak. Now the next one. Obviously, they are living in a carbon is like a house for all these hydrogens. So all those hydrogens will live in one house. They have the same chemical environment, but they have a different environment from a carbon, which is another house. So for these 2 carbons, these 2 hydrogens, although they are attached with carbon, but the carbon is different. Uske neighbor mein OH hai, uske neighbor mein kuch aur tha. So these 2 carbons are different carbons. So these 2 hydrogens have a different chemical environment. So in 2 की 1 peak होगी, उस 3 की 1 होगी. और जो OH के साथ अटैच है वो तो एब्सोल्युटली डिफरेंट हो गया ना. उसकी एक अलग पीक होगी। सो कितनी पीक्स होंगी? 3 पीक्स होंगी, और उनके साइजेस क्या होंगे? फॉर एग्जांपल, एज आई सेड, इस वाली पीक में कितने हाइड्रोजन कंट्रीब्यूट कर रहे होंगे? 3। इस वाली में कितने कंट्रीब्यूट कर रहे होंगे? 2। इस वाली में कितने कंट्रीब्यूट कर रहे होंगे? 1। So this is 3, this is 2, this is 1.
From left to right.
No, that's the placement. I'm going to talk about this later. Okay? अभी मैंने इसकी axis और उस पर बात नहीं की. I just want you to understand कि how the hydrogens give the peak and how their environment is different from the other. So they are going to give 3 peaks, right? And the number of hydrogens contributing towards that peak is mostly, or maybe, not mostly, maybe written on the top. ये जो number on the top written होगा, that will be the number of hydrogens contributing towards that. Okay, secondly, now come to the axis of this graph before I proceed on and give you more examples. आप कह रहे हैं इस ग्राफ का एक्सिस क्या है? इधर तो चलें, आप कह रहे हैं मे बी एब्जॉर्प्शन होगी, हाउ मच रेडियो वेव्स एब्जॉर्ब. इधर टेक्निकली होनी चाहिए फ्रीक्वेंसी, बट इधर एक चीज है जिसको बोलते हैं chemical shift. Now, what this thing is? Chemical shift. So, in NMR spectrum, the absorption of radio waves is plotted against the chemical shift. Now, what is this chemical shift? Now, let me explain it. Come here. यहां आइए. आप कहते हैं जी रेडियो वेव्स हो या आईआर हो या कोई भी हो, उसकी फ्रीक्वेंसी होनी चाहिए थी, एंड दैट इज मेजर्ड इन हर्ट्ज, राइट? और इसका जो केमिकल शिफ्ट का यूनिट भी है वो पीपीएम है, पार्ट पर मिलियन. व्हाट इज दिस ऑल? Now let me explain. Actually, when we place methane and switched on the radio waves, you know, the amount of radio waves that absorb to flip was so low that we were actually not being able to measure it on a scale, the Hertz scale. So then what we did, we have to find a way out for it. So what we did, we use that reference kind of thing, जो हम एटम के मास के लिए करते हैं. एटम के मास के लिए यूनिट नहीं मिल रहा था ना. So what we did, हमने उन्हीं एटम्स में से we took an atom which has the least mass, हाइड्रोजन, और उसके मास को क्या असाइन कर लिया? 1. फिर जो हाइड्रोजन से 2 दफा हैवियर था उसका मास क्या हो गया? 2. कार्बन वाज 12 टाइम हैवियर देन हाइड्रोजन. कार्बन का मास क्या हो गया? 12. फिर कार्बन को ये ले लिया एज अ स्टैंडर्ड और फिर आगे आगे चलते रहे. सेम थिंग वी डिड हियर. हमने एक कंपाउंड ढूंढा, एंड दैट कंपाउंड इज नोन एज TMS, tetramethyl silane, in which one silicon has 4 CH3s attached with it. Now, if I look at the chemical environment of these protons for the sake of argument, how many peaks is going to give? 3 hydrogens with 1 carbon. The neighbor is what? Silicon. 3 hydrogens with another carbon, and neighbor is what? 3 hydrogens with another carbon, and who is neighbor? 3 hydrogens with another carbon, who is neighbor? So all these carbon, all these are attached with. So what does it mean?
Same chemical environment, so same peak.
Yes. So 12 hydrogens will contribute to 1 peak. Okay? And then it was attached with silicon. That's why it would be a unique kind of peak. Because in organic compounds, there is no silicon. Okay? So what we did, before putting this methane, I put TMS here. Tetramethyl silane. And switched on the radio waves. So the protons of tetramethyl silane, they absorb the energy, and you know they give a peak like this. How many hydrogens contributing that peak? 12. So therefore, this peak was huge, like this. And then because of more number of protons, okay? So area of the peak should be bigger, height or width, whatever. So we are now focusing on area. Now, this was a huge peak because how many hydrogens were contributing? 12. Then in the follow-up, I placed methane. And that gave a peak here. And I figured out that methane's 4 protons were absorbing the radio waves 1 part per million, less frequency than the radio waves absorbed by TMS. So TMS ने कितनी radio waves किस frequency की radio waves absorb की मुझे नहीं पता. मीथेन ने कितनी absorb की मुझे नहीं पता. But मुझे ये पता है कि जो मीथेन के 4 protons हैं, they are absorbing 1 part per million. 1 part per million, 1 times 10 to the power -6. Less frequency of the radio wave as compared to the frequency of the radio wave absorbed by TMS. जैसे मैं आप अरीज यहां खड़ा कर दूं, आपका नाम क्या, अवैस को यहां बुला लूं, मैं कहूं मुझे अरीज की हाइट नहीं पता, बट अवैस इज 1 feet taller than अरीज. हाशिम को बुला लूं, he is 2 feet taller. So I don't know their original heights. I know their comparative heights. So this is what we did. The chemical shift is the distance between the peak of proton under consideration and the peak of tetramethylsilane, right? So that is known as chemical shift. So chemical shift is what? The distance between the peak of proton under consideration. For example, now there is a methane and TMS. So every time when you have to take a spectrum, first you put in what? Tetramethylsilane. And then follow up where you put up that proton. So all those protons of methane, ethane, methanol, butanol, all those protons, they absorb frequency from the radio waves as compared to the frequency absorbed by TMS. Or, yes, with relative to TMS. And one last thing, TMS की जहां peak आई, हम वो peak show नहीं करें, वहां सिर्फ 0 लिख देते हैं. उसको क्या कर लिया? 0. And scale आगे लेके जाने की बजाय scale was driven this way कि अगर किसी ने 1 part per million less frequency की radio wave absorb किया तो उसको -1 नहीं कहा, उसको 1 का, फिर 2, फिर 3, फिर 4, फिर 5, फिर 6, 7, 8, 9, and the highest value is what? 80. Right? So chemical shift is the distance between the peak of TMS, the reference compound, and the peak of proton. And we have all the data calculated. Before we go for the analysis, we have all the data calculated, right? I'm going to show it right now. Now you understood what is the x-axis? नहीं अभी तो नहीं, मैं क्लास के बाद तो ये पूछने की जरूरत ही नहीं होती. You know 6 o'clock तक क्लासेस चलती हैं back to back. No please, हमने कहीं बच्चे फिर वेट कर रहे हो. So next is जीशान, जाएं जाके इसको देखें, वो ले जाएं साथ रिकॉर्ड और पेरेंट को बता दें कोई इशू है, चले जाएं, रिकॉर्ड सारा ले जाएं साथ, उन्हें कहीं 6 बजे से पहले तो वो नहीं मिली. ओके सो हो गया. So chemical shift value you understood? Okay, now let me show you. So what we did, we have all the data as I was telling you. For example, look at this. You see what is written here? Typical proton chemical shift value relative to TMS. TMS is equal to what? क्या लिखा हुआ है? So it means the TMS की peak has a 0 value. Now, if it is an alkane, CH3, CH2 or CH, or next to the alkane, the value is 0.9 to 1.7, right? As I told you, if this is the graph, the NMR spectrum, here is the 0, and then goes 1, 2, 3, 4, 5, 6, 7, 8, up to 13. Yes.
Sir, isn't it should be like in negative because
No, that's what I told you. That the peak where the TMS is coming, we assigned it 0. And instead of taking it, although their frequency is less than that, so instead of taking it in a negative term, just like we do in maths, so we took it a positive value on the left side. Okay. So if what is the meaning of 0.9 to 1.7? That if there will be an alkane or any next to alkane, so this is 0, this is 0.9, and this is 1.7. So somewhere here. Okay. And then 2.2 to 3. What about this? 2.2 to 3. So if there is a methane, CH3, that is next to CO, or CH2 next to CO, or CH next to CO, right? So they are going to give the peak at 2.2 to 3. Okay. Similarly, if this is next to aromatic, they're going to give the peak 2.3 to 3. Similarly, next to oxygen, the carbon which is having triple bond and hydrogens attached, the benzene's carbons, hydrogens. And then after this, these were mostly the hydrogens attached with the carbon and next to the functional group. But now below this are the mostly hydrogens which are the part of the functional group. For example, aldehyde wala hydrogen जो functional group में होता है, वो कहाँ पीक देगा 9.3 से 10.5. Similarly, alcohol का, phenol का, carboxyl, amines, amides, these are the peaks. Okay, so this is how you got it. Now, if I sum it up, so now you know the hydrogen is a proton. It is a magnet. It gives a peak, and all the hydrogen contributing to one same environment contribute to one peak, and then their peaks are not random. They have a chemical shift value with relative to DMS, right? And they contribute to one peak if they're in one chemical environment. Tomorrow we'll discuss this, the questions, right? Thank you.